continuation, part 2 of the swing stuff. It's only 10 slides, so don't worry about it. Then we'll talk about events, and then we're going to finish up on events, and then we're going to look at serialization, and that will be our last topic. So I'm kind of going to get this done before noon. Don't worry about it, because I'm going to give you at least 3 hours of study in the afternoon. So we'll have a noon to 3 o'clock lunch/study break for those people who are curious or interested in studying for the final. That's going to start at exactly 3 o'clock. So, and we'll do the attendance before or during, I don't know, there's a ITU person who comes in to do the exam, so I don't know what's going to go on later, but we'll see. Anyway, so let's just finish up a little bit on some of the swing stuff here. Building a set, and this is basically just more examples for you. In fact, probably, you know, later on when you start looking at the swing stuff and you start programming in AWT, and you know, at one point you're probably going to want to look at this stuff later and look at the examples. And I'm not going to go through the source code examples again, but it's nice to see what the capabilities are. Because eventually you'll probably end up building an app that will use something with it. Most things these days are GUI. So we're going to look at, as an example, the simple building of a simple JList, adding and removing items from a JList at runtime, and then making a custom data model, telling the JList how to extract data from an existing object. Why are we looking at JList? Because what we want to be able to do is kind of merge in standard Java programming and list structures and things along with the GUI. So working on how to make things together, because we seriously don't have two components, we have one. We have the Java program. So having the program store the list and manipulate the list and use strings and use data types is important. So what we're looking at in terms of the data model is telling the JList how to extract the data, how to use it, and using strings and toString to display the string with the return of a complex object as an example. So making a custom cell renderer is another kind of theme of this lecture, and telling JList what GUI component to use for the custom cell. So we did this actually in the Android class by looking at custom controllers. So we had a custom list controller, and inside of the list controller we put some items in there, and it was multiple pieces of text or strings along with an image, I believe we put in there. So on the model view controller architecture, looking at the custom data models is a way of changing the GUI control that contains the data. So instead of copying the data from an existing object and putting it into the GUI control, we save it all together. We simply tell the GUI control how to get the data from the existing data. And then we don't have two structures now, we just have one, and it has GUI capabilities, which makes it a little bit more streamlined. In terms of the custom cell renderer, changing the way that the GUI control displays the data values, and instead of changing the data value, simply telling the GUI control that we want to build it using the swing component and represent the data value in the swing component. Good, thank you. You can also talk outside if people want to talk. I just don't want to feel like I'm yelling over you. I like it when it's quiet. So, all right, so some main application components here. We have the JList, the JTable, and the JTree. I'm not going to go through. I'm going to kind of skip through this on the fast side, actually, because it's kind of dry to look at in terms of a PowerPoint. But the simple basic use of the JList is to supply an array of strings to the JList constructor. You can't add or remove elements once the JList is created because it's a GUI component, so you're working with it from a static perspective. But here's kind of the option in terms of how we put it together. If we have a string, and we're going to call the string options, and we're going to say that this is option 1, option 2, option 3, option 4 inside of the string. We can also do this. We can go JList, and remember what I was showing you before. We can cast it to a string. It's a JList. What's a JList? Well, it's a hybrid list that's also swing. So you can take the list that we're going to create, instead of putting it into a list, we put it into a JList, then we have a GUI component of the list. So we can take and use it in the GUI without having to copy it over here, copy it over there, use it. Just one structure does it all. It's going to be an option list. So then the option list is going to have a new JList. And this is the same syntax as we saw before with the options in it. And here's a string of options that we created. So this is how we're going to populate, for example, options for the state. Pick a state, pick an address, or pick an item from the list. Or for a shopping cart, picking an inventory item as an example. And then we can set the visible rows. In this particular case, we can have 4 of them showing, 3 of them showing. If you think about the concept on a state, you're probably going to have one showing, and it's going to be the state of California, perhaps. And then we have event handlers or event listeners, and I'll review that a little bit as well. Attaching a list selection listener, and then using the change to value. You missed the attendance. There's a TA back there in purple. She'll do your attendance for you. Simple JList sample code, where we have a string, and so this is the interesting part here. So we're taking and not using a list, we're using a JList, and so we have a string, and the entries in the string are going to be entry 1, entry 2, entry 3, and then we're going to have a simple list that's going to be equal to new JList, and it's going to be holding the entries, and the entries are going to be the little string we put together, and then we're going to set the visible count so that only 4 of them are showing. And then add a listener. Remember the listeners? Add a listener to the scroll list so that when we select one, we can do something with it. And then on the listener, we have the list selection listener. And we have the value reporter that's going to implement this. So when the value changes, it's going to show you that on a value changed method, it's going to show you which value changed. And this is what our output looks like. So we have the list itself stored in its own JList structure, which is just like a list. But this is the Gooey component that represents the list. And then we can read and write to the list or do whatever we want to. Once the list is shown, however, it's static. We don't necessarily change it. We're going to recreate it, then repopulate it if we're going to change it. But usually that would be, for example, a list of states. Pick a state where the user is going to have a fixed amount in there, and they're going to select something. And then down here on the bottom, if you run through the source code, what the source code is doing is it's once you select something here, it's going to put it down here. So if you click on another item in the list, it'll populate the list selection with the other item. So it's a great way of kind of seeing how the components are working together. And then you're using the container for the JList to actually store the list items in this particular case. So it comes in handy. So we could have changeable sources as well. We can build a JList to create a default list model and then add data to it and pass to a constructor as an example as well. So we can start the same choices as before. We can have like, choice 1 through choice 10 or something. And then we can have a default list model that's holding a string, and we'll call this one the sample model. And then it's going to be a new default list model, and then we're going to add elements. So sample model.add element 1, add element 2, add element 3, and so we can make it grow and shrink. And then we're going to use a JList and to put the model into the JList. So once the list is created, then we populate it out into the JList, and we put the JList out on the screen. So we can use the set visible as well. We can use the same handler as we did before, actually. So here we have the new default list that is created, and it's populated by adding the items. And so this is the same code we saw before, but it's all put together, and it's inside of the example, and we're going to use it to populate the JList now from the list that we've created from the sample model. And then after we've added the elements, it's going to look the same, but we're going to have a little button down here that's going to say add an entry to the list, and we put the entry in there and then adds it to the list. So we can make the list change as long as we build the structure for the list and then populate it into the JList and then show the JList. So it's a separate step that you have to do it in order to make it mutable. But we can make the list change. So we can also use it with a custom data model as well. So we have an existing data that implements the list model interface. And the list model interface maybe has a get element add, a get size, and add list data listener to it. So we can create and build the JList and then set the visible rows and pretty much add and remove items to it the same way we've done in the previous examples, but we can customize the components, maybe add 3 components instead of 1, or change something about it if we want to implement something customized for it. So here we have a method to get the element at, which is going to return the element at, maybe get the size of the element, how many items are in there or something, or how big the element is, so that we can, I don't know, maybe determine how big to put the text field or how big to make a label or something. And then we're going to load some actual data into here. Here's a Java location collection, which is going to be a bunch of locations that are going to be stored in a Java location component. And then Java location has a toString plus 3 fields that are associated with it. So the 3 fields might be neighboring city, a city, or a state, or an area, and then a picture perhaps. And then when we load it into the model, we're going to create a JList that's going to have inside of it Java location as the type that we're explicitly setting. And then we're going to populate the list and put the list out on the screen. So it kind of looks like this, where we have more now. We have more than one component in here. And so we can get the size of this. We can get the component itself, use the component. So basically it shows you how to create a JList with multiple components and a custom kind of data model approach to it. So the JList with a custom cell renderer also. So the idea here is that instead of predetermining how the JList will be drawn on the screen, we can render it at the size of, let's say, the largest elements. Because inevitably what happens here is people have to look at this and go, well, that's how big it is. Let's make this the width. So if you were adding it dynamically, you could check the size and then make this bigger so things fit into it better. If you're going to, for Gooey components, we want things to be expanded out. It's not going to expand out on its own. We have to set the size of that. So here's an idea. So predetermine how this is going to be drawn, and then put the elements in it. And then let's just specify, let's say graphically, which components are going to be used in various different entries as well. So add a list cell renderer. So we're going to change the components that are in the cell. And then add that one to the render component method to determine the GUI component that's going to be used for each one of the cells. So then we can have different things that show up in the different cells as well if we wanted to. So we can get the list cell render component arguments. So one of them is going to be the JList itself. The other one is going to be the object that's going to go into the value of the current cell, an integer, maybe a Boolean. So we can definitely customize that a bit. So here's the Java location renderer that's going to extend the default list cell renderer. And we're going to use a map for that. So now you can kind of see, well, here's a map mixed in. The reason why I'm showing you this lecture is actually to show you kind of the pieces put together. So we have the GUI component with the container components, using all of the the data structures and kind of the ability to make it so that we can actually select an item from this particular list. And in this particular case, we're going to show it into a map, and then we're going to have an icon and a text label and an object that we're going to use. So one of the advantages of the Java utils, especially the map and the hash map, is the ability to put objects in there as well. So it's not just a string or a number, it's an actual object. And the object might contain different components or attributes associated with it. So, and here's how it looks. We have the flag. So we have an image along with a text label that was added to the box. And then the images can be the same for different things depending upon what area, or I don't know, what the object actually contains. So, so it just shows you some custom rendering. So, addition of an image. So in summary, the simple static JList is very usable. You can pass an array of strings to it and use it just as to hold strings or numbers or something. Then we have the simple extendable, changeable JList, so we can add items to it on the fly. And if we're going to do that, we're going to keep a list and then we're going to add it to the JList and then change the list and then update the JList with the new contents, adding and removing data to and from the model. Not the JList. We're using it to the data model that we're putting inside of the JList. You can't actually change a JList. Once it's out there, it's a JList. It's a GUI component that has a list of items in it. So you have to take and create a list of items, put it into the JList, and then modify the list if you want to, and then repopulate the JList with that. So the JList is meant to be the GUI showing of the list, not necessarily the list, but it can be used to store the list. We can also use a custom data model to have this, so we have a real data interface or implements the list model interface itself. We can pass the real data to the JList constructor. And then the ability to make custom cell rendering, to assign a list cell renderer to create and render objects and get properties from objects like the image and the labels and stick them into the JList. So The JList renderer has a method that determines the component to be used in each one of the cells that's going to show up in the list. So, all right, that was a kind of a quick run through on the last bit of the swing I wanted to give you. I wanted to also show you this lecture on layouts. And again, it's kind of a short one as well. We're not going to go through the source code examples. I just want to show you the components that are involved with this. So the topics here are going to be how the layout managers simplify the interface and putting the pieces together using many different layout managers and nesting the layout managers. Standard layout managers, what they mean. There's a couple questions about layouts actually on the exam as well. Positioning the components manually and the strategies for using the layout managers effectively. So this is kind of the conclusion on the concept of the layout managers for you. So we know what a layout manager is, I hope. Okay, good. We know we can nest them. We can put one inside of the other. We can use multiples together. We're not stuck with just one. We can assign to each one of the containers a different layout manager that gives us sizes and positions of the components inside of each one of the windows. We never stick anything inside of a window. We stick components inside the layout managers with the layout managers inside of the windows. So it's helpful for Windows who choose size changes, displays multiple different operating systems. We can choose different layouts for different operating system designs as well. Relatively easy for simple layouts, but surprisingly hard to get complex layouts with single layout managers. So we have to nest and create a hierarchical view of the different layouts in order to actually get it to look correctly. So controlling the layouts and the complex layouts is another topic for discussion here. Used to nest containers with its own layout manager. So you can have a layout manager that has layout managers inside of it that's controlling the layout managers. So different levels of control, which makes it kind of interesting. Using invisible components and layout manager options, and then writing your own layout manager. All you have to do is extend the layout manager class, and you can write your own custom layout manager, just like you can write your own custom list and stick it inside of a JList. And turning some of the layout managers off and arranging them manually as you go through. So simple layout managers, we know we have the flow layout, and it's the default for the applet for the panel and for the J panel. And the behavior here is it resizes components to their preferred size. So it's used to adjust with different size monitors, different size screens, different size fonts, and it's probably the most flexible, which is why it's used as the applet default layout. And it places components in rows, left to right, right to top to down, bottom. The rows are centered by defaults. And we have some constructors for this, and the constructors are the default constructor that just sets everything at 5 pixels between the entries. Don't need to know that, actually, it's just kind of a piece of trivia. But we also have one that sets the alignment, left alignment, right alignment, or we have ones that set gaps for different horizontal and vertical positions in the alignment. So, an example of the way this one looks, so the flow layout looks like this. So we have the flow test that extends applet. And we're just going to put some buttons in there, and you can see how you can adjust the screens here. And we made the screen a little bit bigger. So this is smaller screen, bigger screen. We see we have a word wrapping. So figure flow is like word wrapping. You're trying to figure out the differences. A border layout. That's where we align things associated with the border. So the default is for the dialog box. Also, you can also use it on a JApplet, JFrame. The baby here divides the container into 5 different regions. That's where we get the border, the southern, northern, eastern, western. So we take a look at the compass and we can see we have the different borders of the window. Each region is identified by a corresponding border layout constant, north, south, east, west, and center. And we align things according to the border. So north and south, respectively, are referred to as the height of the component, and east and west are going to be the width of the component, and then center is going to be the range inside the component. So is allowing a maximum of 5 components too restrictive? Maybe, actually. Why not? Well, it puts a little control over it, and then you can only put things in relationship to the borders. So it makes it a little bit difficult to achieve some looks and feels, depending upon what you're trying to accomplish. In terms of the constructors, we can set the gap for the height and the width. We can create the borders of any size we want, or we can just use the default, which will evenly divide out the screen for us. we can add the components. So we add the components to the layout. So we add a component with the border layout region. So add it to the right, or to the west, east. Add it to the west, add it to the top, add it to the bottom, depending upon the border we've selected to use. And we can always specify the region in which to add the component. The center is the default, but specifically explicitly to avoid confusion with other layout managers, we use the center, which is essentially going to be in the middle, but it's not necessarily going to be in the middle depending upon how we've oriented our other items. So here's a picture of what the borders actually look like. So we can put a button, and if we expand the button is going to be the size. It's going to fill up the entire layout in this particular case, because we just set it to fill it. So we have the button on the top, button on the bottom, left, right, and center. So just know that the border layout defines the different regions of the geometry of the screen, north, south, east, west. So. And then we can use that position. So we could put another layout inside of, say for example, a north layout. We could put another layout inside of the north layout and use a flow layout there. Or use, I don't know, another border layout perhaps. So just know that you can divide it out in terms of the hierarchy. The grid layout, we actually saw the grid layout. We've seen all of these layouts in Android. And if you compile, or actually you don't have to compile, they're already compiled for you. If you run the examples that are in the code that's in the zip file that goes along with this lecture, you'll see all of these actually, and you can play around with them and change them. So the grid layout, the behavior of the grid layout divides the window into equal-sized rectangles or grid locations based upon the number of rows and columns that are specified. Then the items are placed in cells from left to right to top to down based on the order of the container. Ignore the preferred size of the components, so each one of them is resized to fit into the grid. So we basically have a generic dynamically set size. So too few components results in blank cells, and too many components results in extra columns. So we have some constructors for it, the number of rows and number of columns. We can set how big the grid should look. Or we can also set the gap in between it. So if we look at the grid here, now we have button 1, button 2, button 3. So they're going to be sized proportionally to the grid location. So you could stick something inside of it, like a flow layout perhaps, and stick multiple things inside of the grid if you wanted to. Or you could simply use the grid as the outer component, which makes it kind of interesting as well. So the one you may not be, because the grid is pretty popular for, actually, if you look at the Windows motif for the Windows 8, it's more of a grid layout, actually. And I would say the border layout is probably the next most popular one, because people like to put menus on the top or on the left-hand or right-hand side. And most GUI interfaces are either a border or a grid type of layouts. The next one is the card layout, which is kind of an interesting one as well. So stacks components on top of each other, displaying one on top of the other, so it's layered. Associate a name with the component in the window. So we have a card layout, new card layout, and we can set the layout to layout. And we have card 1, card 2. So we have card panels, and then we hide and show the different panels of the layout. So here's an example here where we've got the card layout where all of these guys are in here, but we're going to put in here, for example, different cards depending upon which button is being pressed. And we selectively hide and show the different panels that are associated with each one of the cards. So how do we achieve that? Well, we're really creating a panel and calling it a card panel. We're sticking the panel inside of the layout. And then the layout is nothing more than a centered image, so everything's being centered. So we have whatever it is we stick in here will be centered on the layout. So grid bag layout, a little bit different than the grid layout. The grid bag layout divides the window out into grids, just the same as the grid layout, but without requiring the components to be the same size. So in here, the standard grid layout has all the components expanded out to the size of the grid components, to the spaces in here, and then they're all the same size. So now we can make the same concept, but then have this one smaller than this one, smaller than that one, if we wanted to, instead of layering them. So in the card, these are layered one on top of the other. We hide and show specifically for the layouts change with the selections. In the grid layout, grid bag layout, we have different size grids, different size cells. So about 3 times more flexible than the other standard layout managers, but 9 times harder to use, because then we have to figure, it's kind of like when you've ever tried to use tables in HTML and you tried to adjust the column widths or the row sizes and stuff of the tables, and it's really hard to get the table to actually kind of look right without experimenting with it, especially when you resize the screen a couple of times. Looks kind of hard. This has got the same difficulty associated with it. Each component managed by a grid bag layout is associated with an instance of the grid bag constraints that are associated with it. It's kind of like the cell constraints for height and width. So how the component is laid out in the displayed area, in which cell the component starts and ends, and then, because you can have components span multiple cells, very similar to an HTML table tag, actually, using a span. And how the component stretches when extra room is available, and then the alignment of each one of the cells as well. So Java 5 introduced the Spring layout, which is similar power but less complexity. So there's another one called Spring, very similar to grid bag layout, but this was the original layout that was associated with the concept. So you can set the layout, saving the references to it here with the new grid bag layout, and we're going to call the layout, set the layout to the layout that we created. Create some X's and Y's, some heights and widths that are different. Change the constraints on the cells so that we can change the height and the width. And our long story short, after we put it together, it sort of looks like this. This is the example where we have, kind of reminds me of an HTML table. But we have a text area in here, a button, a text area in here, and these are the different grids. And so we're going to change the height and the width. These are a little bit taller. This one's a little bit narrower. Hard to get it to all look consistently, however. And then what are you going to do when there's extra room in here? Then you're going to have, something floated or aligned left to right or centered. By default, the items are centered in this particular example, so it makes it a little bit easier to kind of adjust on the fly. So, and this is the grid bag test, by the way, if you're looking for this example in the sample code. So let's see. Here's the grid bag layout results, where we've got a text field that's up here at the top, and this is the same, using the same layouts. This is the layout field with at 2,1. This is the box field at 2,1, so it's a slightly different effect, but the buttons are essentially in here going to be left aligned, right aligned, but anyway, it kind of gives you the big picture in terms of why you want to use this, because this is a nice application of the grid bag layout, because it's a grid, but each one of the cells is a different size, used for a different purpose. We have different types of components in each one of them. They're not all the same, and they're not sized all the same. We would not be able to achieve this using the non-bag version of this, because then all the grids would look like, boxes. We'd look at a list of icons or a list of text boxes and stuff. So definitely allows for different flexibility. So some strategies for using the layout managers. You can disable the layout manager itself. So you can set the layout to set it to null. If you set it to null, it'll be garbage collected eventually, but you're going to turn it off. So it must be sized and positioned by hand when we set it originally. So we can have it dynamically sized if we want to, or basically position the components itself by going setting the bounds, or setting the size, or setting the location. If we don't have a layout manager in this particular example, we've got some interesting wrapping that goes on here, but we might want the effect, or we might be able to use it for something. So if we set the layout to null and we add 2 buttons and we set the bounds and then we add more buttons, we can kind of see how we can manually, without a layout manager, we can actually manually position the components. A lot of people like to do this because they can't figure out how to use the layout managers. So they turn the layout managers off because you're going to get one by default, and which is going to be the flow layout. So if you don't want it at all, turn it off and then start positioning things manually yourself, which is kind of the hard way of doing it in the long run. So there's no requirement to use a layout manager. So to use them effectively, and that's the other choice, is just turn them off. The other choice is to use them effectively. You're going to have to nest them. So to use them effectively, you have one layout manager inside of another one, as I was mentioning before, and you're nesting it. So rather than struggling to fit the design into a single layout, you divide out the design out into different sections and then use different layouts in each one of the different sections to achieve the look that you're trying to achieve. So let each section be a panel in its own layout manager. And turn off the layout manager for some containers and leave them on for others, especially if you're not going to use them. So it makes sense to do that. And then adjust the empty space around the components so you can have a little bit of buffering, so not everything is like bordered up against each other. And then change the space allocated by the layout manager, perhaps, to make different sections of the screen, larger or smaller. You can do that when you create, let's say, for example, menus. So if the menu is on the top of the screen or on the side, you can change or adjust the space around it so it wraps appropriately. And then use a canvas or a box as an invisible spacer. So here's a way of looking at it, the nested containers as an example, where we have one big old flow layout with a couple of others. So we have a border layout, flow layout, and a grid layout. So the flow layout's actually down here. No layouts up here, and the border layout is over here in the middle section. All of it's inside of a border layout. That's the top part, that's the bottom parts. We're not specifying a right or a left. So that it's not too bad in terms of its ability to adjust it. So most people, when they start using swing, the layouts causes them the most headache because then they can't figure out, well, what does this layout do? Why do we have to use the layout? And then you end up stealing other people's designs with their layouts because you look at that and go, oh, that was a pretty interesting one. I can just use that. And then you have these kind of templates that you'll put together in terms of your design patterns. Because what ends up happening is, if you've ever done any web design, that sort of is the way that things happen to flow. Unless you happen to be a very creative person, you're going to borrow. You're going to look at somebody else's design and go, oh, I like the way that menu looks. And you're going to go, oh, I'm going to put it on the left-hand side too. You know, so you're going to get your designs and your ideas from the layouts. So in Java, however, you're going to have to go and find out, well, what layout are they using? And then how are they putting them in combination to achieve that, if that's what you want. So it's kind of interesting. The result here, this is the same layout, by the way. This is just the layouts that are specified. The resulting window looks like this here, and it's a custom layout. So we have a window motif you'd think would be kind of straightforward, but it's really about 3 or 4 different layouts nested together. So turning off layout management is an example for some of the containers, but not all of the containers. Here we have everything else is put in here. We have some buttons in here, so we have a vertical alignment and the layout's organized. And this one's going to be just open. We don't necessarily need to put anything in there. Maybe it's just going to hold a text box or something. So we can turn off the layout for that if we want to. So in terms of adjusting the space around it, well, you can pad the layouts so you have space in there. And space is going to make it so that the layouts are not bordering up back to back. It's kind of like when you put together a PDF file or a Word file, and you have columns and you put spacing between the columns or a line between the columns to add some special graphical effect to it. You can use a canvas or a box as an invisible spacer, so you're putting in a space essentially. So for AWT layouts, use canvas, and it doesn't draw anything on there. It doesn't handle any mounts events. Everything's empty. Or for swing, you can add a box, which is an invisible spacer, to improve the positioning. So in summary, dragging and dropping swing GUI builders, that's why people use them. They can set the layouts for you, they can set everything. Problem is going to be, if you look at the code after you've created, it's like any other GUI editor, you're going to have a lot of a lot of extra stuff in there. There's a free one, Netbeans Gui generator, built into Netbeans. If you like Netbeans, also available in my Eclipse, not in the regular Eclipse, but there's a special version of Eclipse that has GUI editors and third-party tools in there as well. There's a Window Builder Pro also available, and can be used with Eclipse. So from a commercial product, these are free versions, by the way. From a commercial standpoint, we have JForm Designer, JViter, Speed, whatever, Jiglo, all these different third-party. I don't know how many of these are still current, but you can probably see from the screenshot. It makes your life a little bit easier. You drag the component over, you set the properties of the component, you drag layouts over there, you drag other components, and it does all of the Java code generation for you, depending upon what you've dragged and dropped and stuck on the canvas. So, just an FYI, GUI development tools are available for this. You don't have to do it manually. If you want efficient code that is easy to read and edit in the future, write it yourself manually. If you just want to get it created and you're not going to adjust it in the future and it's just going to be, an easier way of doing it, then use a GUI tool if you want. It's kind of like how people do web development. If you use a web development tool, twice the size of the file, slower, less performance, but you can achieve a lot more without having to know anything. So, other layout managers that are not discussed in this lecture, but they do exist, are the box layout, the group layout, and the spring layout. These are more current ones, actually, the current versions of Swing. Box lets you put components in horizontal or vertical rows and controls the size and the gaps. In fact, if you don't like any of these layouts, you can make your own. That's possible. The group layout groups components into hierarchies and positions them, mostly designed for or used by GUI builders. Yeah, because the GUI builder is going to have its own layout definitions that are going to be used to customize the adding and dropping of your custom components that you're putting in there. Spring layout is used in the most current version of Java, actually. It's an alternative to the grid bag, as I mentioned above. And let you give complex constraints for each one of the components. A few more options, mostly exclusively designed for GUI builders, again. So. This website here will give you a little bit more details in terms of the different layouts. So, in summary, default layout managers for the applet and for the panel is the flow. For the frame and for the dialog, it's going to be the border layouts. What's the default layout for Android projects? Actually, that's a trivia question. It's not a question you really need to know. It used to be linear layouts. Now it's relative layout. So old Android projects used to start out with a linear layout, which was kind of weird because then people had such a problem. Now it's a relative layout. So you put the GUI component when you drag the GUI components on. You say I want it above this one, below this one. So it puts it in relative location. But that's a trivia question. You don't really need to know that, but. For the applet, it's been flow layout for years. Flow layout for applet and panel. For dialogues, it's always border layout because we have the title on the top, we have the OK button in the center, so it's all related to the borders of the screen, the dialogue. Because those dialogues are pretty small, so. Which is kind of interesting. What you need to know for the exam is the concept of what a layout is. You don't necessarily need to know all of them. Preferred sizes and stuff like that, you don't need to know either. Grab bag layouts, stuff like that. So, anyway, that was your concluding thoughts on layouts. I have some concluding thoughts on events to kind of finish up with here. So, events, you can't talk about GUIs without talking about events. In the Android class we went through, and I'm not going to repeat this stuff, and you don't really need to know this for the contents of the exam, but you know that there's at least 3 different ways of putting an event, capturing events. And we're looking at listener as a model view, as a controller, listener controller as a concept. And so the general asynchronous event handling strategy, this gives us our event-driven behavior. So we have the clicks, the drags, the drops. We don't have gestures in Java. We don't have gestures, but we have events. We have gestures in iPhone, iOS. Event handling options, the event handling for separate listeners. So the listener and the observer model as a concept. Implementing the interfaces. So we know that the events are all handled through interfaces. If you don't know what an interface is, then you're in bad shape for the final. But we have interfaces. Event handling for inner classes. You guys know what inner classes are? Class inside of a class. Anonymous inner classes. Do we know what an anonymous inner class is? Well, you're probably not going to know that unless you've taken the Java class. So, standard AWT listener events and sublets and mouse events and different examples. We're going to show you in the next few minutes here. So, determining what type of listener is of interest. Well, that's the interesting thing. We have choices. It's not the same listener. In the standard AWT, we had listener types, and we have basic ones that are used today are going to be the action listener, the adjustment listener, when the screen is adjusted, component listeners, container listeners, focus, item listener, key listener, mouse, text, text typing, text change, window listener. So we can define a class of that type and implement the interface. So we're going to define a class, myListener, extends, I don't know, something, applet, implements, key listener, or mouse listener, or something. And then extend maybe a key adapter, or mouse adapter. So we can extend the listener classes as well as the interfaces. And when we implement the interface, we extend the class. So we can register an object of the listener class as well with the window. So we can say myButton.add the click listener, or add the long touch listener, or something. So using separate listener classes is one way of doing it. And this is very similar to the Android stuff, actually. We can just create a listener class. In this particular case, we're going to create a class called Click Reporter, and it extends applet. And all this class does is listen. So it's going to add a mouse listener, new click listener. So the class behavior is nothing more than a listener. And the listener is out there looking to see what component we add it to, and then listening to see if that event actually occurs. So here's a separate case here where we've got a click listener that extends mouse adapter. Mouse adapter is a class because we're using the keyword extends. So we have a click listener that's a subclass of that, and then we can attach it. So we have a mouse pressed event that's going to be defined. When we press the mouse, we're going to see something. So it's going to report mouse clicks. So if the click listener wants to draw a circle whenever the mouse is clicked, it can do that. It just picks up the event, and the event handler draws the circle. So why can't it just call the get graphics to get the graphic object for which to draw? Well, then we don't know what that one might be. So we add the listener to the component. We use the component to control the draw, to control the graphic, because these are all different components. So a general solution here is to call the event.getSource, which is I just described for a button as an example, to obtain a reference to the window or the GUI component for which the event originated from. Cast result to the type of the interest that we're interested in handling, and then call the methods on that reference to do something to the graphic, to change the background color or do something. So here we have an add mouse listener is going to be equal to a new circle listener. Well, what is that? That's that class we just made a few minutes ago, or I showed you the code for it. We didn't really make it, but that what extended a mouse click listener, and then we can add the listener. If we add the listener, we can use it out here with a mouse pressed event, and on the mouse pressed we have an applet, and we can have a reference to the applet, and then applet get graphics, and then we can use the applet to draw something to the applet to change it. So we click this here, and it changed that applet over there, changed the background color or something. And this is what it's going to do actually. It's going to lift up, create the applet, and put a smiley face, and so draw some circles inside of it. This is the same draw example we looked at during the second weekend of the course that showed us the 2D draw stuff. It's part of the 2D draw stuff. It's also part of the example set if you download the source code that goes along with this lecture. So this was implementing it as a separate class, and we could also implement it as an interface. And if we implement it as an interface, we just implement the interface, add the methods for it. So I have the shape interface. If you remember from the shape example we gave you yesterday, we have get area, and we have a circle class that implements shape. You can implement many different interfaces. So we can go shape, comma, mouse listener, comma, something else. So of the interface, the benefits of the interface, just to review the concept, the class can be treated as an interface type. So public interface shape, implement shape, circle implement shape, rectangle implement shape. So it gives us multiple inheritance, gives us multiple types. So here we have shapes as a new circle, new rectangle, they're all shapes. So it gives us part of the relationship that is established between all of the different types of shapes that implement the same interface. That's a little bit of review for you. So here we have the source code for the mouse listener and the mouse adapter. Well, we make them into interfaces, and then we can have an adapter and a listener all implemented by the same class. So we can bring in those multiple components, which is why we're using an interface for this. If we have multiple components, if we don't, we can just turn it into an extended class from it. So here we have the interface mouse listener, and then we have the class, abstract class, mouse adapter. So we know that these two are different items, that the interface here is implemented by the mouse adapter. So we're going to include the methods from the interface in our implementation, and we're also going to implement the abstract methods of the abstract class. So in case 2 here, when we're implementing a listener interface, we implement the mouse listener, and then when we do that, we're going to add the mouse listener to this. We know what this is from yesterday or from the last couple weekends. So here are the methods that are part of that interface that we're implementing, and it's going to be mouse entered, mouse exit, mouse release, mouse clicked. And then on the mouse pressed, we're going to implement the method to do something. We're just going to draw a circle, it looks like. So adapters versus interfaces, and then we have the method signatures. The method signature has to match exactly to the interface. If it doesn't, we have a problem. So if you goof on the method signature, in this particular case, we have, as an example, mouse pressed with a lowercase p instead of an uppercase p. We overload it instead of implementing it. And then if we don't put the @override method annotation on it, we end up with no error messages at all, but we have functionality that doesn't work because we didn't implement the interface. Instead, we created a new method and called it something else, which is the same example I've been going through the last couple of lectures with the @override information. So unless we tell it explicitly that we're overriding it, compiler's not going to know the difference. It's not required for compilation, but if we put it in, we can check, and then we can make sure we've actually implemented the interface. It's a generic problem that we have with interfaces in general. So an interface should give you a compile time error if it's implemented correctly using the override. So the adapter has no compile time error, but nothing happens at runtime when you press the mouse click if you don't put the @override in there. So the solution for adapters is to put the @override in there. So when you think you are overriding a method, put the @override in there, a line above the start of the method, and that comment that you're putting up there will tell the compiler that, hey, I'm overriding. So it knows that you're overriding. If not, it's not going to know you're overriding. If it doesn't know you're overriding, it's not going to do anything for you. So what's it going to do for you is going to error check for you. So here we have the circle draw one that extends applet at the override. Says, hey, I'm going to override the init method. Here we have one that says, hey, I'm overriding the mouse pressed method. I'm not adding a new method to it, I'm overriding it. So if that's the case, you're going to end up with the overrided method, so you'll get the method that actually works and it implements the interface correctly. So just the same way, we can also put a named and an anonymous subclass or an inner class inside of the class. It's not a subclass, it's an inner class. I didn't mean to say the word subclass. If we put a class inside of a class, it's not part of the inheritance. It's an inner class is what it's called. So it can be defined inside of another class. Can you define an interface inside of an interface? Sure, why not? Can you define an interface inside of a class? No, it's two different things. Can you put a, yeah, this is the answer to that question. Can you put a class inside of a class? Sure, why not? If I put a, who said static? It's not static. Static? It doesn't have to be static. You can put an inner class inside of a class, and it can just be regular. It can be, but it doesn't require it to be. Yeah.
Class is class, but we can have static in a class.
Why would you put a static inner class inside of a class? There's a reason why you're going to do that. You hide the method. You're hiding the class, and you're hiding class methods inside of that class, which makes you required to use it through the outer class. You can't get to it outside of that class. So it's hidden from other classes. But if you don't want that, if the class is only going to be used by the parent class, I shouldn't say parent class, outer class, if you create a class inside of another class, it's an inner class. If it's only going to be used by the outer class, cannot be used by other classes. It's not visible. That's why I say, why would you make it static? It doesn't really matter. You make it static when you want to have it used at the class level through the class. So you have to go parent or outer A dot inner A dot run me, if the name of the method was run me, if it was static. Because everything static is used at the class level, not at the instance level. However, it doesn't have to be. You can make an instance of a class that includes another object inside of it. So the outer object gets created by the instance, and then you have an inner object that also is owned by the instance. Why would I want to do it? What if I had a checkbook object, and inside of my checkbook object I have an inner class that's a check? It makes sense to nest that inner class inside of the outer checkbook class because it belongs together. Can I have checks outside of a checkbook in this application? Nope. So I create a new checkbook, and inside of the checkbook I have checks that get written. And then I can organize those checks inside that they belong. They're inner objects of the checkbook instances, which makes it so that if I have checkbook number 1, checkbook number 2, checkbook number 3, all these checks belong to 1, 2, and 3, and they can't be mixed and matched all over the place. They're not visible. So it's a way of designing an application where if the inner class only works with the outer class, nest it as an inner class. But in theory, you're never going to do that. So you're going to have the objects on the outer level. You're only going to nest it when it can't be used or shouldn't be used for confusion purposes. You want to make sure that that class, the inner class, belongs to the outer class. It can be static, doesn't have to be static. If you want to make it a class level and make it static, it doesn't have to be static, though it can be a regular. You can have many different objects as well. So you can have more than one instance created. So I have checkbook number 1, one instance of checkbook number 1, but I got 50 checks in there, or 60 checks in there. Those are all sub-instances of subclasses. I should not say word sub. It's not sub. It's inner class instances that are created inside of the main outer class object. So it's kind of interesting how inner classes work. A lot of students will hesitate putting a class declaration inside of another class declaration, but it's possible and it's usable, and it does come in handy for certain design things. So there's no restrictions. It's just like everything else. And you can put an interface inside of an interface as well. You just can't put an interface declaration inside of a class or a class inside of an interface. They're two different concepts. You can put an abstract, and this is the interesting part, you can put an abstract inner class inside of a non-abstract outer class. But if you have one abstract method inside of a class, the whole class has to be abstract. But you can have an abstract class defined, and then that method, that class, inner class, cannot have an instance until it is defined. It has the same rules as an outer abstract class. So if it's a base class, you have to wait until it's implemented, and you have to implement it in every single one of the inherited classes that comes from that. That is rarely done because it's too complicated. So no one will do that. They won't make it abstract. Don't make it abstract. If you're going to use it, implement it. If not, turn it into an interface and implement it later.
Another
Yeah?
clarification here, as you had given the example of when we use an inner class, and you've told static inner class will, the only difference will be how we access the inner class, right?
Correct.
In the outer object and then the inner object.
Yeah.
Any scenario when we exactly use it, or just the access way is different? That's why we use a static inner class.
The only time you're going to put anything static inside of a class implementation, whether it be an inner class or an outer class or nested, it doesn't really matter. All scenarios work the same way, is when you want to access that method or access that data from a class level. It's the only reason why you're using the keyword static. Usually, if you want all instances of the class to share the same information, you make it static. Or if you want all instances to run a particular method, you make it static. Yeah. And you don't have individual methods for individual instances, you only have one method. So it's kind of like taking object orientation and taking off the object orientation part. But you have objects that are communicating with it because it's a member of that object. So if I have a person object and the person has a ID, a static ID, each instance can take a copy of the static ID and increment it or change it to make it part of their ID, and they can have a non-static piece of data that works with that static data by copying it, working it. Because what you're going to do is you're going to take the current value. So if I have a bunch of 5 people, the first object that gets created, and I have a static ID, and the static ID is a simple integer, starts out with 0. Object number 1 will have 0. Object number 2 will see 1. Object number 1 will see 1 as well. But they took that 1, well, back when it was 0, and they made it their ID. So they have a non-static ID that's based on a copy of the static ID. So that when number 3 comes around, the number is now 2. Everybody else sees 2 if they go back and look at it, but they already got their own IDs. So number 3 is going to take that and make their current ID equal to that ID, and then number 4, number 5. So that's how we use it for check numbers. So going back, we could have a static check number. I would put that static item though inside of the check inter class that's inside of the checkbook outer class. And so each one of the checks, if I have this instance is going to have checks that are going to start with the same, can have the same numbering, why not? They're in different objects. So then I can keep track of that same numbering system for checks or something, which is a great way of abstracting it out. So, okay, so that was a nice little review of inner classes and outer classes. Here's an example of what you're looking at here. You have an inner class, and an inner class is defined inside of the outer class. And in here we can put the interface on the outer or in the inner. Doesn't really matter where we use the interfaces, actually. So we have named inner classes, and then we have unnamed interclasses. Yeah, so the named inner class is just like the outer class. The unnamed is attached to a method that's a class declaration. So here's the named inner class, where we have this listener here that's going to be put on for the mouse listener. So we have circle listener, extends mouse adapter, we have mouse pressed. The anonymous one, it just has the method body of the class but no name. We get this with the, in Android, we get this with the action click listeners, button press. It's click listeners, actually. Here we have mouse pressed. We don't actually have a mouse on an Android system, so we'll never see this, but this is for the Gui, AWT, and swing stuff. So, and here we have a new adapter. Can we have an anonymous instance of an object in Java? Not on the exam, but just a trivia question. Can we have a a non-referenced instance of an object in Java? Sure, why not? So we know we have a reference when we say person P1 creates a reference. We go person P1 equals new person. We have our object that's created as well as a reference. So if we just say new person, just like we did new mouse adapter here, we have an anonymous object that's created. It's anonymous because it doesn't have a reference to it. But it is an object. It got created. If we're not careful, we can turn it into garbage. But we have automatic garbage collection, so we don't have to worry about it in Java. But long story short, we have no reference to it. That's why it's anonymous. If we have a reference to it, then it's not anonymous. It has a name. And so it has a reference variable that's pointing to it. So that's how we create the linked lists, by the way. We have references that refer to item number 1, item number 2, item number 3. Then we have anonymous memory that we create that we point to it and say, hey, this is going to be number 1, it's going to be number 2, it's going to be number 3. We just move the pointers around. We change the list order easily. So as a concept, we can do the same thing with anonymous inner classes. Why put a name on it? It's an inner class that's inside of another class. It's just going to be used for something. So we make it anonymous. And just make, and then here we have a mouse adapter that's going to be anonymous in this particular case. Summary of the different approaches. We have event handling strategies that work with them, and we have the pros and cons of the separate listeners. And this is very similar to pros and cons we get actually with Android. So if you're interested, you can it applies both ways. So separate listener, advantages of it, you can extend an adapter and thus ignore unused methods. Because we know if we have an interface, we have to implement all of those methods, whether they're used or not. We have to put in method bodies and actually implement them. If we don't, if it's a separate class, separate listener, we just ignore it, just don't use it. You can pass arguments to the class constructor if you're actually creating an instance of an object. If you're not creating an object, if you have an interface, you're not using a constructor at all, actually. Separate class is more reusable. It's more extendable. It can be extended, can be reused. Disadvantages, you need an extra step to call the methods in the main window. If it's a class, you're running methods on the class. You're running methods on the objects. You can use a main window that implements an interface instead of using a class for the listener. If you're doing that, the advantages are there's no extra steps needed to call methods in the main window. It's already there for you. Disadvantage, you must implement the methods. If you're using an interface, you have to implement all those methods, whether you're going to use them or not. That's why you can see all these empty ones that says, from the implements overrides, actually you'll see at override, and you'll see mouse press, mouse push, mouse up, mouse down, all these different, and then they're all empty. And if you don't put them in there, you get a compiler error, because you have to implement them as part of the interface. Hard to have multiple different versions since you can't pass arguments to the listener. It's an interface. You only have one version of it. So, event handler strategies, pros and cons in terms of the inner class, the named inner class, and this applies not towards pros and cons of the inner class, but for event handlers that are implemented via interclasses. The advantage is you can extend adapter and thus ignore unused methods. Very similar to using a class, actually. No extra steps needed to handle the methods and can be determined by you can define a constructor and pass arguments to it because you are extending an inner class and not an interface. Disadvantage is a bit harder to understand. Inner classes in general are harder for people to understand, which is why a lot of students won't go that route. So they'll make it an outer class even though it belongs to that class. Anonymous inner classes, advantages the same as the named inner classes. The class itself is even shorter because you don't even have to give it a name. Disadvantage, harder to understand, not reusable. You can't reuse an anonymous class. Can you make an anonymous class, not an object, but an anonymous class outside of a class? Can you make an outer anonymous class? Yeah, she's got it. No, you can't. Every object has to have an identity associated with it. It goes back to identity, state, and behavior. So you have to have it has to have an identity. Otherwise, it can't exist. But you can have an object that has an identity that is an object that doesn't have a reference to it. That would be a unnamed instance out there. You have to just say new person. New person will actually create an instance of a person. How are you going to run methods on it? You can't. There's no reference to it. But you can say...
Constructor, we can add some services.
You can actually. You can use the constructor when you create it. Even without a reference to it, you can call a constructor when you create the new instance. And you can set it so it does something. Why are you going to do... Actually, here's another... It's not on the exam, but why would you ever want to do that? Ah, you got it. Background, yeah. So yeah, that's an easy question, I guess. Background process, services, threaded. So if you create a threaded, multi-threaded, and it was an object, you just say new person. It just runs. It's going to be running. It's created, and it just runs, and it's in the background. There's no foreground processing for it. It's threaded, so it'll run along with everything else. So they'll just run as a background process. You do that in networking scenarios. Synonymous interclasses, the advantage is the same. So hard to read, hard to use well. Alright, so event handler details and examples here. If we kind of look at the standard AWT event listeners, we're looking at this variety with action listeners, component adapters, focus adapters, key adapters, and then registering methods that are associated with it. Add an action listener, add a mouse listener, stuff like that. In terms of the details of it, the action listener handles the buttons and a few other actions that are associated with it. We have the action performed. So sometimes people look at this and go, well, that's where the naming is coming from. It is. The naming for Android is coming from this. Adjustment listener, component listeners. You don't actually have to know all of the different listeners. In fact, nobody out there really knows all of the different listeners. It's associated with whatever application you're building and whatever purpose you're trying to achieve. In terms of the standard event listeners, container listeners, the focus listeners as well. Item listeners, key listeners, listening for key events. Think of these more like signals. Anything that's going to generate a signal is going to be a different listener. So an activity on a mouse, activity on a keyboard, a game console component, a pen, they're all going to be listeners. And you'll have special libraries and utilities or APIs for different interfaces that aren't standard on the regular computer hardware. So if you put for example, you attach a keyboard for music or something, music thing, piano keyboard, you can put a listener on, register a listener for the keyboard. So same as you're registering a listener for a mouse. So what button was pressed? This button was pressed, will then generate this sound. So you can easily create a controller for a piano or for any game console or any device, which is used a lot for Java gaming, or game consoles, stuff like that. So you're just adding another listener, so when you press the button, after you load the driver on for it, register it, add the listener, check the listener on this event, put some picture on the picture, when you press this button it does something, this button it makes a noise, kind of thing. Which is it's called a listener model. So you're adding a listener from a driver. A driver that's controlling the hardware. Drivers are generally models that control hardware. Listeners control events. So text listener, window listeners. Simple whiteboard here. So this is also another example in there where it adds a mouse and a keyboard for putting something on a canvas, and the screen looks like this. You're adding a listener to draw a line when somebody presses with the mouse on the canvas. So it's a whiteboard that's being created. It's capturing events that are occurring. So this is actually an applet, and it's one of the examples, simple whiteboard.html, that is included with the source code for this. Adding keyboard events, well, you're going to, instead of drawing with a mouse pointer, picking up the point of XY point in the grid and then drawing lines and shapes and things, you'll just be putting the keyboard character out there. So now you can draw some lines and then pick up the keyboard event and actually capture the captured key and put the text out there. So, which is how you're going to mix the two of them together. So mouse event details in here. In terms of the listener, it's the location of the X and the Y of the click that you're interested in getting, and so that you can use it for something. You can also pick up the multiple clicks, double clicks, triple clicks. You can actually click up the button. So you can right mouse click with the right button, mouse click with the left button. Using the wheel is also part of the library of a standard API. And again, the driver for the mouse has to be loaded to actually identify, and it's operating system independent, which means all of these click listeners, especially for keyboard, for mouse, is going to be part of operating system controlled events that are occurring, which means you might get different results on different operating systems depending upon your implementation, which is kind of interesting as well with the Android platform, because the presses on the sensors, the presses and stuff on all of the hardware is inconsistent. It's not predictable, which is interesting because then you can get different APIs that work better on different platforms because they have different controls and different listeners. So something might be more attuned to a Motorola device versus a Samsung device, and then you can get the special libraries for that and load on different API versions. So combining listeners, you can also do that as well. Spell correcting text fields as an example here, where you have a key listener that corrects the spelling during a typing, and then an action listener that completes a word on an enter, and maybe a focus listener that gives a subliminal hints when you put the mouse over. So in summary, what do we got here? General strategy. Here's to determine what type of listener you are interested in finding. Check the table of standard types and see what's available. Define the class of that type. Extend the adapter separately if you want, or implement an interface, or extend the adapter in a named inner class or in an anonymous inner class. Register an object for the listener class with the window. And then understanding the listeners is half the battle. What are you looking for when you get it, and then how you're going to respond to the listener event once it's captured is, again, another part of the battle. So we're not going to worry about the later topics because I'm not going to continue with this, but that's everything you ever wanted to know about the listeners. I have one small mini lecture here, 13 slides on serialization that I want to present to you as well. This is going to be the last of the slide sets. Then we'll have a lunch break. Then we'll have some study time for the final that you'll take this afternoon. So we really only have about a half-day lecture kind of going on here. But this one's called Serialization if you're interested in it. It's actually kind of interesting. It has examples of looking at and using GUIs and file systems with GUIs, sending GUI across networks, working as the object and sending and receiving data as objects, or objects as data, I should say, which is kind of interesting, actually. It's more of a networking kind of thing, but you don't need to really have to understand networking to understand how serialization is happening. So what does serialization mean? Java lets you send arbitrary complex data structures in a single command. So you're going to write an object from an object output stream. So you can write text to files, sockets, processes, almost any type. So you can have an array type, an array, a panel, anything that can be nested as well. Custom classes must implement serializable. So you implement, it's an interface, you implement serializable, you add the implementation for the methods, and then you can work with objects instead of streams of text and stuff. Java lets you create complex data structures as well in a single command. So here we have a read object from object input stream. And then we can read from files and sockets and processes. When you compare Java serialization, also compare Java networking with other languages, then you see that power of Java in terms of how it's automated and how easy it is compared to other languages. So it's definitely easy and simple, which is why people prefer to use Java for a lot of these different types of projects. So the requirements, well, you need a top-level data structure and all of the internal components that must implement serializable. So if they're all implementing serializable, they're all abiding by the same interface, which means they all have the same behavior and you can use them all the same way. So you can send one object to another object and you can use the objects intermixing in the same context, which makes it a little bit more flexible. So this is one of the reasons why interfaces are used, which is why I'm kind of implementing or showing you this introduction to serialization. It's one of the main reasons why, well, not one of the main reasons why, but one of the good examples for the use of interfaces in general in the language, outside of making something abide by protocols or rules. Most built-in classes already do this. They already implement serializable. Those would be all of the different components that we looked at, even the containers, so array list map, they all already implement serializable. Primitives are okay inside the data structures, no need for them to have wrapper classes either. They're all serializable. So integer, float, double, string. So make your own class and implement the serializable. It's very simple. You just implement serializable. There are no methods. So there's nothing to implement, which is the tricky thing. It's just an empty serializable. So bottom most non-serializable class must have a 0 argument constructor. So the parent of the first serializable class. So the object is okay. Both ends must see the same version of Java, so you have to use the same. So if you're going to send something across the network, you got to be running on the same JVM and the same version of Java. Both ends must also have the same version of the class files, so compiled in the same version of Java. So it looks like it's sending data as an example. We can wrap an object output stream around any regular output stream. So for a file as an example, file output stream, file out, we'll call it file out. It's going to be a new file output stream. I gave you some stream information during the second weekend. This is just an extension upon that concept. We create one here with file out, which is file out. It's an object. It's a file object. So we're sending an object with a new object output stream. So instead of taking an object, taking all the data out of the object, sending the data, creating a new object on the other end and populating that object with all this data, we just send the object. So if you remember anything, just know that serializable allows you to send and receive objects across network connections. Also allows you to work with objects within the same application. Use an object as a component, and it allows you a lot more flexibility, and it's more efficient. So you can send a top-level data structure here, out.write object the data, and in this particular case, the data might be the object that we're writing. So you can send data to files. In this example, an example of an array of shapes. So here we have a try, and we have all these bunch of shapes that we're going to create. And each one of the shapes has got a rectangle and a circle inside of it as an example. And then here's the code here. So we have an object output stream out, which is going to be equal to a new write output stream file out, and then write it out. What are we going to write out? We're going to write out shapes. So it takes your objects and writes it out to a file. Why do you want to do that? Well, because you have an object-oriented program, you're going to read the objects back in, maybe into it from a file. So it does actually create sort of some flexibility in terms of the application design. When are you going to do that? Whenever you want to reuse objects. But if the person has a program, as an example, that creates checkbooks, and inside of the checkbooks we have another object, and those are checks. And the person closes down the object-oriented program and shuts off their computer and comes back the next day and opens it back up. Do you want to recreate all those objects? No. Save them and then load them back up. So that's how we keep persistent data with objects. What else are you going to do? So people go out of their way to take these objects and put them into a database, put them into a text file, do all this stuff with it, when all you have to do is just save the objects. And then when the program loads back up, just take those objects and load the objects back up into the program, and voila, you're back where you started from. So you can save it in a native form. There's no translation, there's no manipulation, there's nothing. Just open and close your objects and use your objects over and over again. Which is why I'm showing you this lecture. Actually, it kind of shows you the ability to work from the object level instead of the primitive data types and the file I/O and all their database stuff. Can you do this on an Android system? Sure, why not? Is it done all the time? Yeah. Because how else are you going to save the data in a game? You know, you have winners and losers, and you have scores and stuff. One of the approaches, not so often used, however, because a lot of people, this is what I'd call more advanced in terms of concepts. People are afraid to do that. Instead, they'll create little text files and they'll stick them on the SD card. And then they'll open up the file and read in all the stats, and load up all the objects, create all the objects, and then populate everything instead of just saving the objects. So here we have a bunch of shapes that we created. We're going to save the shapes, and we're going to write it out we're going to write out the object to this output file, and then we're going to close the file, and then we're going to do some file I/O checking. So we can send data to sockets. So when you start working at the Java Enterprise Edition, which is the course you usually take after this course, we start out with this concept, and we take objects and we send them across networks, and using RMI and some of the other technologies that work with the object as the component instead of like raw data. So sending data to a socket, doing regular socket. We're not going to cover sockets in this class, but if you wanted to, you can write it to an open socket. You can receive the data from a socket. So a socket is nothing more than a stream abstraction that you're going to connect to a port on a computer. So we have the object input stream, socket in, socket out file. So it's just the same way as you're reading and writing it to a file, you can read and write it to a socket. Reading data from a file, well, we saved all the checkbook stuff. Let's bring it back in. So shapes is going to be equal to shapes in.readObject. Give me the objects we created last time you were here, and load them back up and put them into the shape. So we can just use it like regular old file I/O, but instead of it's file data, it's object data. Reading data from a socket, writing data to a socket. So we have an array of shapes in this particular case. Sending entire window to a file or to a network. So we have a savable frame is the name of this example. So we have a main frame, and by the way, if it's serializable, it can all be done the same way. We can save Gooey components, we can save frames and windows and things and reload them back up. Anything, if it's an object, everything in the language is an object. We can treat it the same way. So in this particular example it's called savable frame. We have a main frame, and the frame is already serializable by default. In fact, most of the items are, when it comes to Swing and AWT, all those items are serializable. The frame has an internal field in it representing the height, the width, the colors, the layout manager. We have two sub panels in this example, and the panel is already serializable. And we have some buttons in there. We have a custom button listener, also serializable. The button listener in this example explicitly implements serializable. It wasn't serializable to begin with. And then we can send to and from a file by clicking on the save, and then we can send to and from a network. So here's the custom class that's created for this, and the base code is going to be in savableframe.java. And then I believe there's a screenshot coming up of what this thing is actually doing. There's a lot of code in here. So we can send the entire window. So somebody creates a window of something, and let's say, for example, it's a chat program. You know those interactive, I'll go back to the whiteboard concept, those interactive things where people log in. They could capture the whole screen and load it on their system instead of loading it from the network location. And we could send it back and forth and update it, and then synchronize the screen so that they can add something to the screen that's on their local computer and then send it back and forth among all of the different chat clients or something. So this is just saving the screen information instead of saving the object. It's the Gooey component. It's the same thing. It's an object, a JPanel object actually in this case. So here we have a machine 1. We're going to run the frame server 8888 on the port, and then on machine 2 we're going to run the frame client, and we're going to go back and forth. So we have a client server application in this particular case where the client is connecting to the server and loading the server window and sending the information back and forth. So it just basically demonstrates that the serializable concept also works with the Gooey components as well as the object components. It allows you to create some pretty advanced user interfaces that are GUI based, as well as the utility of being able to save and load objects. So the summary here, we have the class format. Make sure that the custom classes implement serializable if you want to do this, and the parent is non-serializable class has a 0 argument constructor if it's non-serializable. Object isn't serializable, or object, excuse me, is already serializable. Blech. Sending data, wrap an object output stream around the raw output stream, and you can save an object and then write out the object, write object you want to send back and forth. So you need to use a try and catch block with that. Actually, Eclipse will warn you if you're not using it, make you put one in. So, in terms of receiving data, you wrap an output input stream, object input stream. I can't talk today, around a raw input stream. And then you do the opposite. You call the read object instead of the write object with it. And you cast the result to the desired type. You do have to cast it correctly. If you're reading in an object that's a person, you have to write it to a person reference object or use it in the terms of its object identity. You get the whole thing. So you get the person as well as everything else inside of it when you're saving. You're not just saving the current object, you're saving the object memory that's being occupied by the object. So I'll leave you with that because that's where this course the next course, if you were to continue on with this and go on to Java EE Enterprise Edition 1, we take the core Java set, we start out with serializable, and we move through sockets and TCP/IP and datagrams, and then we move into networking for remote method invocations, and then the ability to load an object from remote and connect to objects that are not on the current system. So we look at distributed client-server models in terms of using Java cross-platform, cross-systems, cross-network. And then that class also covers the concept of servlets and JSP, and it goes on to the enterprise, which is the networking components. So serializable is one of the main components that's a bit foundational kind of. Being able to send and receive a serializable object is what you're doing, especially with RMI. Everything's serializable because how else are you going to be able to invoke, an instance of an object? So why people go that route instead of just sticking with the core Java and using other networking technologies is that when you network this together, we can take advantage of the same concept of the JVM and the Java working environment. And here, yesterday I mentioned as a kind of a side point, we only have one instance of one object that we're using out there. We're not constantly creating more instances of more stuff and linking it. It's kind of like the difference between the C++ exe file and the Java class file. One of them is loading everything it needs, it's statically bound, the other one's dynamically allocated. So we take those objects now, and instead of linking to objects that are on our single computer, we run across a network, like RMI as an example, as a platform, middleware platform that connects our objects from different computers. So the accounting program just handles the accounting, and the database is just the database. And we can put in beans and things in between to manage the connections and service up the objects. So when we log into a web page and we run a remote application, each client who logs in isn't making their own instance of every object that they're using. They're using one that's already created. And so if it's already created, then it's housed by a manager that keeps track of it and allows clients to connect to that object. Very efficient. For economies of scale, you can have thousands of connected users with the same efficiency as one. So you're not using the network traffic and you're not using the resources. You're using a manager to keep track of all the objects and then serve them up, which is how servlets are working. So that part, everything past, this is what they call core Java because it's just the Java foundational programming skills. Once you have that, then you apply it to networking, and then that's when you can really make use of Java in terms of what it's good for. Standalone application development, it's okay. It's used in Android all the time. But mainstream industrial use, networking components. That's where it has. That's why people choose Java for the networking part of it. So I will leave you with that in terms of the end of the lecture part of this long weekend courses. So let me cut this video.